All right. Hello, everyone. Welcome to today's talk. The first one being by Nik Murzin, who's going to tell us who's rather going to give us a demo, a walk-in demo through Wolfram language, tools, functionality, and so on. Now, most of you know Nik, and therefore he doesn't need much of an introduction. But in any case, there may be certain things about his varied and broad life that you may not have necessarily directly interacted with. So, of course, Nick's originally studied physics, but later on he worked at IBM. But his interests have spanned from physics, mathematics, computer science, web development, machine learning, technology, and he's been participating in several hackathons and so on. In just the way that we love physics, he loves physics as well as programming in a very deep sense. And among the tools that you see, besides the physics tools, one of the important things in the Wolfram technology world is this quantum computing framework. Nick is one of the key contributors to that. Also, the hypergraph backlet that you saw yesterday with Carlos and Nick, they co-developed it. So he has been at the forefront of many of these developments and tools that you're using, and he has a unique mix of having this intuition to kind of combine research in math, physics, along with his computational skills. So we're really lucky to have Nick. One day we'll actually see him face to face, but right now he's that enigma who's available on Discord whenever we want to answer any question you have. So thanks, Nick, for being here, and we're looking forward to a very interactive talk.
Thanks, Xerxes. Also an introduction, I could have done better myself. So, yeah. So, okay, let's just start. So, the plan today is just the plan. I usually do it like 2 times a year, some kind of demo, live introduction to all the tools that we have in the physics project, like all the hypergraphs and all types of graph multiway systems kind of things, right? But the goal primarily is basically to answer all the questions that we already gathered up to this point about all the terms that we've been floating around in the physics project and graphs. Of course, I have like some basic examples and that I've prepared, but here I specifically left the empty section for questions to just code them in during the presentation if you have some specific question how to do that or this and like all the things. So without like further ado, we already have kind of regretfully I don't see people who were primarily asking questions like, oh, Miles is good. He's here. he was asking a lot of questions, so it's good he's here now. Maybe will continue doing it. But okay, the first thing I'm gonna talk about is hypergraphs. There are 2 kinds of hypergraphs that we have in our vicinity of the physics project. There's like a Wolfram model. So I'm gonna give you just like crash course 101, not like the full introduction. We had a good lecture given by Max this winter. So this is like a link to that lecture about his set replace packlet, which is available here. This is like the whole very extensive documentation about all the properties and functions that are available there. But like just the basic thing is just there's like mainly there may be 2 functions that people should care about. They're already not part of the packlet that you can install separately, but they're part of the resource function repository. So they're immediately available by just by tagging them by its name and resource function, right? As soon as you do it, you can immediately like construct your Wolfram model rules, and the rule plot would understand them, and they can actually show you them what is the left-hand side, the right-hand side hypergraphs when you apply them. Another thing you can obviously do, you start evolving this rule, starting from some maybe given input hypergraph or some automatic one. Automatic is like some default one that looks like the left-hand side of the given rule, something like that, and the number of steps that you would evolve. And the result of that code is basically some object that then you can query. So it's like a bunch of, let me actually run it. So this is the evolution object. This is like all the properties, maybe not even all, there's maybe some hidden of them. But the few of them that you should learn is like the base one is just, if you evolve this hypergraph, the initial hypergraph with a given rule, you can obviously want to extract the list of states at each iteration. So this is like just the list of hypergraphs. If you want to plot them, like maybe the first 5, this is the hypergraph plots, which is you can also do manually by, for example, from that one of that function that I just told you about. If you do this and give it like maybe this hypergraph, like just hypergraphs is basically represented as a list of edges, and each edge is just a list of vertices. So that's how we can easily plot it. There's a bunch of options that you can provide in order to customize all the styles and all that. Right. So another thing, of course, after evolution, this evolution object also can render causal graphs, which shows you all the interaction, which I'm going to talk later about how this causal graphs actually being constructed, because it was major confusion. But here's like, if you want to dig deeper, I think there's like to actually reconstruct some of those events yourself and maybe do some customization. I think like this is mostly the main parts of the data structure underneath this evolution object. It's like you can list all the events, and I think this is all the events list, right? And all the edges that were introduced in the process of evolution. So then like, I think like this index is just indexing into this list, right? I think it's like this is maximum number is 32, and I think here you just have 32 edges. So basically this is just recording the events by all the edges that were evolved during the evolution. Yeah, oh yeah, this is the example of plotting with some option that I just told you. And this is basically the 101 of Wolfram model. Okay, so if you have a question about Wolfram model, now is the best time to ask it. If I of course know the answer, because it's not my primary code.
Does the evolution function work on ordinary graphs or just hypergraphs?
The ordinary graph is just a special case of the hypergraph. So yeah, of course, it's like if you have a graph, then you just form it, turn it into, like you can actually generate random graphs, like this maybe. This is just, you can turn it into a list of edges. A list of edges is just a list of undirected edges, but if you want to really turn it into the similar structure as hypergraphs, you can do it something like this. So this is like now hypergraph edges, or hypergraph rather, immediately. So you can feed it to plot function, and now it's using the hypergraph rendering functionality. So obviously edges doesn't have to be higher arity than 2, or lower arity than 2. All right. Okay.
When you apply a number of updates, it's doing the multi-way like every update. Is that correct?
No.
No,
the Wolfram
just one.
model is primarily single way. There's a way to specify ordering, there's the whole. Let me find some. Yeah, event ordering function, right? There's the whole thing how you can specify different ordering. There's like some named ones. I don't think that you can specify a custom way, but there's like a you can order your application by newest stage. You can do it by random. Yeah, there's like plenty of built-in orderings, but the point is that Wolfram model just picks one application.
There's no way to specify my own ordering function, or there is?
I don't think in the Wolfram model you can do it yourself.
Okay.
Yeah, there's no like it's not trivial to actually come up with a way for user to specify what application to choose. It's like, well, you can just apply all of them like at this particular way, and then you can feed the whatever output to the user, and then maybe whatever the output, maybe he can filter it out, but it's not obvious. And I think like Wolfram model supports this. It is supported in the next package, multi-computation package that I'm going to show later a little bit, though I don't quite remember how to do it from the top of my head, but we can figure it out. Okay. So yeah. So again, this is just the evolution just happens in the single way fashion. So some particular application was chosen if there's some ambiguity. Okay. So that's the Wolfram model. But there's another way to do hypergraphs and hypergraph rewriting. This is our effort with Kagros. This is like short for Wolfram Institute hypergraphs. This is like just published as a packlet. You can install it from the repository, or this is like a development version. There's some bug being fixed there. more frequently. Even today, I fixed a few just while preparing these examples. So yes, this is how you install it. This is how you load it, and you basically can construct hypergraphs. Similarly, you don't have to specify the list of vertices. You just specify a list of edges, but now you have there's a different way of specifying it. This is just a shorthand for your binary edge, like in a graph. So if you don't like this list, you can use it like this. And there's like a little bit generalization of the Wolfram model. We also allow nullary edges because it kind of makes sense. If you want to generalize arity, there should be 0, 1, 0 vertex edges. So that's an example of 0 vertex edge. This is a unary edge, this is a binary edge, this is a ternary edge, and so on. Right, so this is how you construct a hypergraph in our institute version of the hypergraph. Okay, but usually we do it not by hand. There's like some nice widgets for drawing hypergraphs. They're a little bit jerky, so I apologize in advance that like it may be cause some bugs and all that, but it can have some basic functionality to draw some edges. And I see some comments. If only one result is chosen per evaluation step, and that affect the causal graph derived from it. Well, the causal graph is single way, right? If you even the single path in the branchial graph can produce non-trivial causal graphs. I'm gonna show the causal graphs later. We can go through in detail how those being derived from just one rewriting step, so that you can see what's the point of that construction. Yeah. So the point is that causal graphs can be non-trivial even in single way evolution. Okay.
In your hypergraph above, only one of those edges is directed. I mean, the 1, 2 edge is directed, I guess, but then the others are undirected. Is that?
By default we assume the unordered symmetry. So that's another different thing about this Wolfram Institute hypergraphs. We assume that all our hyper edges by default are unordered, and we obviously have this generalization of notion of edge symmetry. So in the Wolfram model, all the edges were ordered. So basically, whatever sequence of vertices in each hyper edge you specify, that's the order of those, right? And it is fixed. Here we wanted to generalize this notion. I have like more examples about the edge symmetry a bit later. Maybe I can skip ahead a little bit. Yeah, so that as I said, so by default all the edges are unordered. Yes, so if you make two hyper edges like that, there's no arrows, and you can specify a symmetry like that. This is like globally specified that every hyper edge is an ordered one. You can do it more targeted, like for example, here you want to specify that only this edge is ordered from 1 to 2. So that keeps this one still unordered. And another way of doing it is by annotating some edges explicitly like that, like a special wrapper, which is like so you can do it by option, which is just a list of rules specifying which edge has a typical order, right? Or you can do it like this. And generally you can, if you're talking about edge symmetry now, the generalization is not just about ordered and unordered. You can basically specify symmetry as an arbitrary permutation group. So for example, you can, like when we do this symmetry, let's call this hypergraph, call this HG. You can ask what is the symmetry of that hypergraph. This is just in the order of hyper edges specified. When I say order, there's no symmetry, there's no cycles, so there's nothing to order around. But this is by default is unordered. So now we have like this two generators, two cycles that generate the full permutation. So we can order those vertices arbitrarily. So that's what we mean by this edge is unordered. If I add an additional vertex like that and ask what's the symmetry, there's an additional generator. So that's basically like a permutation group specified by 3 generators that allow arbitrary permutation of 4 vertices within this 4 arity hyper edge. Okay. If you want to specify like a arbitrary symmetry, for example, I can say, actually, I want to be able to only permute these two vertices, first two vertices. This is not referring to the vertex indices. This is referring to the order, so it's gonna refer to this pre-4, right? So if I ask it, it's gonna remember that the symmetry of this hyperedge is this, and this is gonna. It's not rendered in any way. We kind of still confused about how we can like put arrows on the hyperedge to identify which can be cycled and all that. So it's without confusion, but it's there, right? And the symmetry of hyperedge is gonna matter how the rewriting is done. And I guess I can show the example here, like a more simple example. So for example, how does symmetry affect the rewriting? So we can skip all the, this is not interesting. Or I can show the widgets. Before rewriting, I can show you how they actually draw things, because I haven't actually finished. So this is just a nice widget that you can do. Call and draw edges. You just click, 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 create new vertex. This is like indicates the selection of each vertex. Then you press E or space, I think it also works. Yeah, so sometimes it's a bit jerky around, like doing some beeps, but in the end it just draws the edge. You can select it like that, it starts flashing. You can right click it and there's some options. Maybe you can recolor it. You can relabel it, we call it F, maybe A, you can order it, and you're done. Hold on, I haven't ordered it. Okay, now it's ordered. Okay, and as soon as you finished, you can print it. Now it's a hypergraph object, right? The hypergraph object, basically, it's a hypergraph under the hood with many options, right? But if you, what I press there is like Command Shift I for the input form, right, and Command Shift N for the standard form, and also Command Shift T for the traditional form, and it's just like simple direct product of edges, so that you can, if you want to insert it in somewhere when you want brevity, so you can use traditional forms of hypergraphs. But the standard form is just render it as a plot like this. Another way of using that widget is more helpful in practice is to press return, and then it just immediately replaces the widgets with whatever hypergraph is. And then you can, all the hypergraphs have this simple context menu, which is just a single item, just drawer, and you replace it with widget, and then you can edit again, and then return again, then see your edited hypergraph. So that's what you can like, I'm gonna show next, like how you can actually apply. I guess the plan was to show it here. So in addition to like, to having, okay, now it's too big. Let's make it like this. All right. There's also a bit more advanced widget for drawing rules, so that you not individual hypergraphs. Let's make a simple rule. All right. So we have this. There's like one button just to copy everything from the left-hand side to the right-hand side. You can remove it, remove this edge, and maybe draw binary edges like that, right? And there's again the same kind of thing. You can print the rule, and it's just going to be printed or return it. Now this is like a hypergraph rule object. We can keep it here. We can call this thing a rule, right? Okay, let me just actually also print this thing, the hypergraph. And okay, now we have the input, which is like just to show how simple rewriting works. So we have a thing called rule, which is a hypergraph rewriting rule, and the input hypergraph. Now, in order to apply it, in order to start rewriting, you just simply apply the rule to the input, right? And then the return is maybe a little bit unexpected, but it's like a bunch of hypergraphs, but actually it's a list of associations like this, which basically shows you that there are 6 ways you can rewrite it. Why there's a 6 ways? Because by default, as I said, hypergraphs are all unordered, and that's transitions to the left-hand side. And on the left-hand side, is basically if your hypergraph is reordered, it means that this hypergraph would be tried out to match like in all possible ways, right? So that's why there's like a permutation of 3 factorial. That's why there's 6 different hypergraphs, which is in the end the same form. But if you dig into actual structure of what this hypergraph, what is the matching and rewriting done, there's going to be slight differences. Like the main difference in this case is going to be like this option, which shows you what were the map between left-hand side vertices and the actual input hypergraph vertices. So we can deconstruct all of this information and see what actually been written. Right. Question. Combinatorial explosion. Well, yeah, if you're that's what hypergraphs are in a way. You have to be very careful if you don't want ambiguities and maybe pick some particular path, like in the Wolfram model case. That's why Wolfram model case were able to produce the large hypergraphs that you see in all the universe in the Wolfram Physics Project, because we ignore all the ambiguities, pick some particular order, and that's why there's no combinatorial explosion. You just have a single hypergraph at each time, right? But if you want to make it carefully and then in the maximum generalization, then you have to consider all possible ways you can actually do the rewriting with whatever rule specification you provided. So that's one thing. Actually, let me try to change this so that, for example, if we make this hypergraph, hyper-edge ordered, and you're going to run it, I think it's still going to produce. Oh yeah, so by default we also assume that we match edges with an exact symmetry specification match. So ordered match, even though ordered edge can't technically match on an ordered edge, we not allow it by default, because, well, just because it's better default behavior, we concluded. But we can ignore the symmetry method. I think that's how you do it. Yeah. So if you ignore this constraint that the symmetries has to match exactly, when you try to match the ordered edge on the input hypergraph, there's only a single match. Yeah, Flo, have a question.
Here with the rule function, we're only applying it once, right? And is there an option in the
Yes.
rule function to apply it, say, n times?
No, there's no rule function. It's just like a simple application. You can write it yourself. It's not very complicated. You have to basically nest this procedure, and you extract this hypergraph key and then apply it again. Actually, it's a good exercise. Let me try to do it. Well, we have to have a good rule that applies at least twice. Well, let's make one. Why not? So let's make a similar rule that Karos had. I think I already have it. Let me scroll down. Actually, let me make it from scratch. It's not complicated. So let's make this a rule that Karos were making yesterday that does the composition, right? So assumes that you have two ordered edges, right? And we just remove them and make a single ordered edge instead. Something like that. Okay, so that rule being applied to some hypergraph like that, with multiple ways. Let me see, like maybe with multiple vertices. Well, is it drawn? Yeah. It's like some buggy behavior. Okay. Well, I guess we can keep them unordered. No. We're gonna apply it with this option. So let's check whether actually something happens. So if you do it like that, nothing happens. Let's try by ignoring the symmetry. Okay, we have the few of them. If you apply this to this one, you can do it again. So if you were to write it like some nested thing, you can like use the nest graph function, which expects to have a function, right? Like that, I think. And this is your input, and then you say how many times you can apply it. So that's one. Yeah, we have to do actually to extract the hypergraph key out result. I think that's how we can do it. Let me see what it echo it out. All right. Maybe this has to be in a list. We just seen that there are multiple of them, not two. what this returns. Yes. Where's down now 1? I'm a bit confused. Did I copy? Oh, that's the wrong hypergraph. This is after rewriting, right? So that's the free edges one. Another 2 of them. Okay. All hypergraph. Oh, so okay. So now this shows the application. So we can customize this nest graph so that each of the vertex rendered as a hypergraph and all that. But now we can apply it twice, and now we have a graph. So technically, in each vertex there's a hypergraph. So it's not too complicated to do it yourself. Whatever iteration you want, as soon as you have an ability to actually perform the rewriting. Okay. So
Hey,
that's
Nick,
an example.
in your, this is just a question about hyper edge ordering convention, but when you have like a 3 edge and you ordered it, why do we have like 2 arrows along the side, but then there's like a side sort of that doesn't have an arrow? I'm just not familiar with that convention.
Like here,
or
right? Like this one.
yeah, for instance, yeah, I see 2 arrows there, but then there's sort of like another side of that.
Because we want to indicate that this whole hyper edge of irity3 is ordered. So we want to specify that the first one is the first vertex is the first vertex. This is the second. This is the third. So this is like our attempt to identify that it's the arrow size is changing and it's growing, because it was if it was ordered in a different direction, we have to also specify.
And ordering, I guess it makes sense that you don't assume that in some sense it's like cyclic. So that's why there's no 3 to 1.
Yeah.
I see.
It's not cyclic, it's just order is fixed
Yeah.
completely. Cyclic could mean there is some permutation symmetry. Yeah. All right. Yeah. So that's how you do the rewriting, and potentially manually making multiway systems without using any tools. This is just me. This is just to show you that each hypergraph contains all of those annotations. No, you don't have to worry about it. So forget about this. This is if you want to annotate or customize the styles of your hypergraphs, this is like one of the few options that you would need. Like another feature we also support is you can tag each edge. So it's very similar how edges work in built-in graphs, where you have to, for example, if you make an edge like that, you can do directed edge which is tagged, and you basically can provide the same option, right? And now it's a tagged edge, which usually the tag is being just purely decorative, but tags in the Wolfram language graphs usually is helpful for annotating like multi-edges. Like this could be a tag number 1, this could be a tag number 2, because without the tags, it would be problematic, for example, to style them separately, because like you would have to do, for example, I want this edge to be red and it's working, right? And I want this edge to be green and it's okay, right? But if there wasn't any tags on edges, there's like this wouldn't work. Okay, so it's like picked out this particular annotation and decided to style them, and it works for any kind of annotation, not just styles. If you want to label edges, there's a similar problem. If you want to style, label, and maybe some custom annotation of edges if you want. So there's some problem with multi-edges, basically what I'm trying to say. But in the hypergraph, we were kind of decided to try out a different approach. So you don't have to tag it. You still can use tags that can be helpful in order to separate multi-edges, but technically you can remove them, right? And if you remove that one, let me see. Okay, maybe I was lying. Okay, it was working at some point, but there was some idea to support this, but not anymore, I guess. Okay, ignore it. Ignore the previous comments. Yeah, the idea was to support this kind of more weird annotation when just the ordering of edges are taken into an ordering of annotations are taken into account somehow. But yeah, for now, just remember there's some kind of annotations that you can provide the hypergraph, which work similar to how you could provide symmetries for each edges, labels, and so on. And labels, by the way, is also another thing that can be useful for rewriting. So I already showed this example of symmetry, how symmetry affects how rewriting is being done. But there's also labels that can be useful here. I already drawn rule, but now you can use basically labels of on your edges like as patterns in the Wolfram language, rewriting, right? Because Wolfram language is based on rewriting, so it makes sense to kind of make it very similar as much as possible. So if you label your hyperedge, like here, you label it with a symbol with the underscore, now this label acts as a pattern. So if this rule acts on this hyperedge with the label A, right, it's gonna use this A as an X here, and this right-hand side of the hypergraph would pick it up. So it's going to be applied, and that's what you can also manipulate labels together with the rewriting of the hyperedges. So, and this is like analogous to this kind of thing. But in the usual rewriting of your expressions, you can kind of only construct tree-like expressions. Here you basically can have not just trees, but this arbitrary, more complicated connected hypergraphs.
So in order to match that pattern, the X underscore, your input hypergraph needed to be 3 vertices with these directed that it has a directed hyperedge. Is that correct? And then you label, there has to be some label on the inside, and like
it doesn't have to be labeled by default. All the labels are assumed to be none. So if this
so what happens if you change that?
Yeah, so if
what happens if you tried to put in a different hyperedge that isn't a 3 arity hyperedge, or does that just not work at all?
No, it's not going to be applied.
It won't be applied. Okay.
It's like a buff. It's just if there's no match, there's no match.
Yeah.
But if there's some particular match, like in that structure, for example, when I showed this complicated associations, I have an example here, right? When I showed this association that specifies what actually happens during the match, you can see that there's also some additional rules. Like this is like symbols. This like for convenience, V's are for vertices, L's are for labels. So for example, if we actually look at the association for this rewriting here, let me call it A again, before, right? So you can see that this X matched to A. So here it is already, right? So it's just an additional symbol binding that we gonna construct when your labels contain some patterns, right? So this is basically a list of rewriting that then can be applied to all the labels on the right-hand side. And that's how we treat labels. I hope that answers it. If there's no match, there's not much. Okay. Yeah, so what else do we have in this hypergraph packlet? We have a bunch of things to enumerate graphs and random graphs. Well, they're not very interesting and a little bit buggy, so I don't want to show them. But another like interesting thing that we've solved in this packlet is canonicalizing these hypergraphs. Well, I wouldn't say we solved it, but we kind of made it much more general. For example, if you try to canonicalize a general multi-edge graph in the Wolfram language, it's going to complain immediately and say, okay, it's not implemented, right? It's a bit annoying. You can't even do it for graphs, but we want kind of this notion of canonicalizing hypergraphs to make canonical versions of each hypergraph for arbitrary hypergraphs, multi-edges or not, right? So it's even more general than multi-graphs. And we did support it, and under the hood it like works with some, well, there are multiple methods. There's some slow ones that use some combinatorial way of trying to canonicalize, and there's a very simple one that I think we still don't understand whether it works correctly or not, but in practice seems to work. It's let's convert this hypergraph to a graph without multi-edges. So there's some nice procedure that you can of this transformation back and forth of hypergraph and graph, and then you can canonicalize this. So you basically piggyback on this one canonicalization of graphs, but not general ones. And then you can deconstruct the graph out of it.
What is a canonicalization of a graph? I don't even know what that is.
So if you know about what isomorphic graph Q is, or the way to the problem of comparing two graphs in general, if you like have a graph, two graphs, and you want to figure out whether they're isomorphic so that you can map each vertex on the one graph to another vertex on a second graph, it's not a very trivial task, right?
Right.
So you can think of it as what would be the canonical transformation so that you can rewrite all the vertices of each of those hypergraphs to some unique one, so that then you just compare it one by one, like purely structurally. So
is it kind of like a net for a geometric object? How you can kind of like decompose into triangles or rewrite it in different ways?
Which object do you say?
Oh, no. I was saying when basically if you could rewrite the graph in different ways, is it kind of like a net from a geometric object? You can kind of lay it out in different ways.
It's not about rewriting. It's just like the topology of the graph. It's not trivial, right? It's like if you're not given the coordinates, how you embed it on the plane and all that, you just hand it a list of connections between edges, and you handed it two graphs with this connection. There's no trivial way to compare them. You don't even know whether it's the same graph or not. You just handed the connections between vertices, right? They can be labeled differently. They have different names, but topologically they can be the same. And this is the problem: how to figure out whether they're actually the same. That's what the problem of isomorphic of graph isomorphicity is, in a way, right? Given these graphs, look, they look identical, but they're isomorphic because you can map one vertex to another. And similarly for the hypergraph, you have the same problem, right? How to figure out whether they're the same. And the canonical graphs is just it's like an intermediate algorithm. Like the isomorphic graph can be formulated in a way that, okay, in order to figure out whether they can be mapped to one another, just make a canonical version of each and then just compare it exactly, because you have to canonical graph makes, like, well, what the name suggests, a canonical version, so that there's canonical version of each vertex name. So then you just have to compare how the edges look. So it's like, so orders all the edges, rewrites or renames all the vertex names, and that's what you have to compare at the end.
So it's kind of more like identifying a knot. Like a knot may look different, but two knots might be the same depending on how their loops and tangles are.
Yeah, you can phrase it this way. It doesn't have to be a knot, just a graph, right?
I'm just trying to grok it in my head for something that I might be more familiar with. Thank you.
Yeah. So basically, it's a problem how you would rename all the vertices and reorder the edges, so that if the graphs are actually isomorphic, this reordering and renaming would produce the same thing, right? So that's the procedure. So that's what canonical hypergraph is doing. It just figures out how to, for example, this. If you take the input form, you can see that there's some names. If this hypergraph, like this label vertex could have been, oh, it's already like a XAB or something, whatever it is. Let me try to make the labels more obvious. Right. This like hypergraph contains two hyper edges just on top of each other and three vertices that are named randomly. As soon as make a canonical hypergraph, it's like ignores all of that. And now the names are canonical in a way that it's integers in some order. And if you take this particular hypergraph with some different order of edges with the different vertex names, you're going to get the same result, right? So that then you can just compare the list of hyper edges and you're going to be sure that they're the same. So that's a purely combinatorial problem that I think we, to some degree, solved in the Padlet. Okay. And that was were hypergraphs. And the next I'm wanted to talk about like how to, with all the multi-computation kind of, all the multi-computation talk about how you can do the multi-way rewriting in all possible ways, all different kind of graphs you encounter in those multi-way systems. What do they mean, including the causal graphs, right? This is like, this lives in a different packlet. It's multi-computation packlet, similarly to how hypergraphs were installed before. It is a packlet in the repository. There's a development version. This is how you can install it, and you can immediately construct these examples. There are multiple types of multi-way systems. So even before you start rewriting things and constructing graphs, it produces an object. So it's in a way very similar to Wolfram model evolution object, but now it's a multi-way system object, which also contains a bunch of properties that you can query. Not a lot of them. It's mostly different kind of graphs that we've defined within the physics project. Right? There are multiple types of objects that you're rewriting, like strings, hypergraphs, Wolfram Institute hypergraphs, which is just if you can construct multi-way system by just providing this hypergraph rule that you can draw and the input hypergraph, right? And it would make this object that then you can use to construct different kind of graphs. So for example, if this is the string multi-way system with an input string with a couple of rules, you can run it for 2 steps and make an evolution causal graph. This is actually rendered a little bit more clear than yesterday covers for showing when there was not or Hatem before that, when it wasn't clear what's the input, what's the output. Here is basically each event shows you what was the part of the string, which characters were the input to the rewriting rule, and what would the output. And if you mouse over each of those objects, there's like much more to say about how it is structured. It's a bit, you can see that each string under the hood is actually represented by a hypergraph. So each character is basically turned into a hyperedge. Each event is some more information similar to the information that you have when you apply a rule to an object, and it provides you with all the information about what actually happened. But we can dig in a bit more detail. But the first thing, I guess, to understand what is this data structure under the hood of this whole rewriting. Because one of the motivations to write this multi-computation packlet was to unify all these systems like strings, hypergraphs, lists, cellular automatons, whatever, expressions in general, under the simple type. And the type, of course, was a hypergraph because it was very natural. It was a little generalization of that, so that it makes more clear to distinguish different types of hypergraphs. And I called it linked hypergraph. And it's basically a hypergraph where each edge has a bit more information about what's going on. So it's like it's linked because each first vertex is always some kind of link indication, and the second vertex is the arbitrary data. So for example, if you want to turn a string into this linked hypergraph, you do an obvious thing. You turn each character into a hyperedge with like incrementing the link index. You put each character as a payload, and the children of each character links to the next character. So basically, if you plot it, like for example, well, you can make a hypergraph out of it like that. It's going to be like make a string of ternary hyperedges that linked by consequent vertices. Like this 2 is linked to 2, 3 linked to 3, and so on. So that's like how the data structure works for all types of rewriting and causal dependency extraction from the rewriting, I guess. Right? There's like more examples and you can do it backwards, of course. You're constructing strings. You can do it for arbitrary expressions. Now it's not necessarily sequences. It's basically a tree, like an expression tree, like that. Right? It's a very simple tree. You can nest it even more deeply, maybe HPC, like that. Right? So if you turn this into a linked hypergraph, it's going to be again this object where edges are of this form, but now they maybe contain more than one child because it's a tree, right? So if you turn this into a hypergraph, you'll get this, right? So they're all labeled now, all labeled by some payload implicitly here. They're just not shown.
Just curious, is there like any kind of data structure that doesn't fit into this? Like, it seems incredibly flexible. Can anything be a hypergraph?
I think technically yes, right?
Okay.
As soon as you have like this, it's just maybe the matter of efficiency and so on.
Yeah.
If you are able to, if all in the Wolfram language is very natural because every expression is a tree,
Mhm.
right? As soon as you know how to turn trees into hypergraphs, that's it. So then you can say everything that's serializable as a Wolfram language can be turned into hypergraph.
Yeah. Nice.
So it's very flexible in this way. But why we do it is that these links that link hyperedges to each other, they are very natural to specify causal dependency, right? So you can, this is like just a little bit more examples how to go back and forth. This I already showed that you can construct multiway systems out of the hypergraph rules and input hypergraphs. So the first graph you can encounter before going to hypergraphs is, of course, the evolution graph. This is the same rule that we had above, that composition rule that just replaces two edges with a single edge. If you apply it once, right, it can be applied in 3 different ways. Here we're dealing with ordered hyperedges, so it just can be applied on different pairs of 3 pairs of hyperedges. So you can immediately see what this does, right? The evolution causal graph would also put an additional vertex, making it like a bipartite graph with 2 kind of vertices, where you basically replace each edge that corresponds to an edge with a separate vertex that renders it in a more clear way what it actually happened. So here you can.
Why was there not 2 directed edges in the evolution graph? Yeah, so I'm supposed to be replacing 2 directed edges with 1 directed edge, but when I see like on the left, say like the left application, why are those not both directed edges going from 1 to 3?
It may be because, let me try to evaluate it. Oops. Is it this? I'm not actually sure. Maybe it's a bug. Who knows?
Okay. But they should both be directed, right? Based on what you've given us here. I think.
Yeah, this is basically should be directed because this one is directed.
Yeah, exactly.
And this is one of the things I've tried to fix before this live stream, before this lecture. I thought I fixed it. Or maybe I broke it. I have broken it. I'm not sure. Yeah. The event actually shows the correct thing, I think. See?
Oh, yes. Okay. Yeah.
Yeah. So I definitely fixed this one, but I
Okay.
guess I haven't. It's still broken.
Okay. Great.
Okay. There's some subtlety to actually render it correctly and extract the object. If you see that this, yeah, the symmetry maybe is not correctly constructed, because we're not directly dealing with these objects that have all this built-in symmetry. We turn them into this linked hypergraphs, which is just a list of vertices with some payloads. You have to somehow propagate the symmetry correctly. It's not trivial. Because you don't care about like, because you want to also determine how whether there's some causal connection between those events. Yeah.
Can I ask a quick question?
Sure.
Can you go a little bit up? Yeah. A little more up.
Yeah.
Where's the rule?
The rule?
Yeah. So, for example, 1 to 2 and 2 to 3 goes to 1 to 3 and 2 remains alone, right? In that rule. Yeah. So when you apply here, please go down a little bit. Yeah.
Mhm.
So this, for example, the bottom left, 3 to 1, 2 remains alone. So shouldn't there be only 1 to 3 only? Why are there 2 lines between 1 and 3, even though one of them should have an arrow, as you said? But
Yeah, well, let me do this at first. So this is just the raw application of the rule, right? It doesn't like use all the multiway stuff. Here, what we're doing, we are picking two of the edges. For example, the first application took this 1, 2, 3, two edges, 1, 2, and 2, 3, and turned it into a new edge, right? So that's why there are 2 edges. There was already one edge from 3 to 1, and then we
oh,
collapsed
I
these
see.
2 edges.
Okay. Thank you.
Yeah. And we did it in 3 different ways.
Oh, okay, got it. Thank you.
Right. So here we have correctly the direction. It's just like in this multi-computation tries to be clever, but not always succeeds. All right. So another types of graph people talk about, like branchial graphs and causal branchial graphs. They're a bit slightly different. The branchial graphs we will discussed are defined by some ancestor information in the states graph. So in this evolution graph, basically, two states are connected by a branchial edge if they have a common ancestor or immediate ancestor, I would say. So here you can what this shows, right? Just connected by a single edge. So you have a complete graph. So it's a very simple example. But you can also have the similar notion for the events. And now it's a bit more physical, because now you can talk about events as have some special separation. Like we talk about, because events, we talk about like events in space-time. So now instead of, in addition to talk about events as time-like separated and space-like separated, if the events happen in different branches of the multiway system, we say that they are branch-like separation. So those edges between events now, not states, are branch-like separation between events. So that's kind of this type of graph tries to construct this object. Okay, is the branchial graph like the siblings? Well, we already
Carlos was
discussed
laying
that,
it out.
right?
We were using the term siblings and stuff. I'm sorry, please.
Yeah, it's like there are many ways to define it. Like when it came up last time, I also mentioned there's a branchial hypergraph generalization, right? It doesn't have to be just the immediate ancestor, right? It's just it's not a graph at all. It's a hypergraph. So you can define what is the relationship between different vertices in the graph based on their ancestry and make a new hypergraph. So it's a bit more tricky, but it's like a very generalization of this notion. So this is like an example of the branchial hypergraph. But yeah, what we mean by branchial graph, just branchial graph without any causal prefix, is just an immediate ancestor. So it's more like a, I guess, sibling graph between two vertices in some particular slice. There's also some notion of the slice, how you would slice the multiway system. When you cover the evolution, it's obvious what the slice is, because you know what the input was the input hypergraph, and what would be the next hypergraph produced by just applying your rewriting rules once, and what would be the new hypergraphs when you apply it once more, right? That would define all the layers, even though they can be linked together in loops and all that. But this operation of just constructing it under the hood kind of defines you which vertices are contained in which layers, even though they can be looping around, and maybe you can have the same state appear in multiple layers and things like that. But you can basically ask question whether in one particular layer, as soon as you like just produced a single layer of new hypergraphs, and what is the sibling connections between them. So that's the note.
But I'm sorry, but we're not limited to just a single layer, so to speak.
You can, yeah, usually it's like we did, like in the physics project definition, we usually construct branchial graphs for layers, right? But you can just take a union of all of them and call it, okay, that's just the branchial graph for the multiway system graph, for the whole multiway graph, when you just have the same vertices as the multiway graph, not constrained to a single layer.
Cool. Sounds like a combinatorial explosion at some point.
In what sense? It's like this is just the graph notion that we kind of just trying to push, or just have at least a name for it. Like as soon as you have a graph, in this case, usually it's a multiway graph, you can just construct this new graph that based on the ancestor information, right? Whether that's like for each pair of vertices, you determine whether they have an ancestor or not. You render the edge between them, right? And you can do it for all the edges and make a new graph. It's going to be a graph with the same number of vertices, but with a different kind of edges. So that's just like a purely graph notion.
Gotcha.
So branchial graph makes sense to me, but I'm having a hard time understanding causal branchial graph. How do I know when I draw an edge between two events?
Yeah. So if you mouse over this this information, you can see that there's a the tree position, right? So for example, if you mouse over this one, the tree position is list 1. This is list 2. This is list 3. So that's basically the that's data that indicates where the origin or maybe the index of the branch of that event is, because at some point, well, here it's like the immediate. As soon as we have the single input, we apply this rewriting, right? And because the ambiguity, there are 3 possible outcomes, we create 3 branches, right? So that so we immediately tag each of those events, each edges in the multiway system by some index, right? And that's what we're going to call like a branch index, right? So that's like the data you can assign to each event.
So it's basically just, if I look at the evolution causal graph, does it have a parent evolution node or whatever, or is that correct? If I just look at this, I can see those 3 all have the blue node as a parent.
Yeah, it's basically as an input here.
As an input, okay, yeah, sure, input.
So this is just like always the edges in this evolution causal graph. The events are always just replacing edges in this evolution graph, right? And you can also attach this index, because we have this ambiguity that we produce 3 outcomes, right? In the single way evolution, like in the Wolfram model, we will pick a single outcome, one of those 3. But here we want to record all of them, and we just simply assign an index. And this is like the tree position is there, because if you apply it once more, the tree position is going to just be a list in the tree. So at the end of the day, you produce a tree, right? And you want to record where in that tree your event appeared. And depending on this position of the tree, you can determine whether they in the same branch or not.
Yeah, right.
Right, branch was separated. Or
Can I ask a quick question?
Yep.
Why are there no arrows on the top 3 lines, but there are on the bottom 3 lines here?
On the bottom 3, like here?
Yeah, going from the top blue box to the yellow middle boxes, there are no arrows.
Or maybe they're just hidden.
Oh,
there should be arrows, you just don't see it because this frame is too large. Or something.
Okay, thanks.
Let me actually try to. Yeah, sweet. Usually there's like nice trick to know for graph rendering. If you do performance goal quality, this is just an option to all the graphs rendering in the Wolfram language. It kind of tries to see what the actual rendering of which vertex is and try to determine, okay, it didn't work. Usually it's like a bit clever and it knows that this like overlaps with an edge. Maybe you can do edge style or something different. Arrowheads. If you change arrowheads, how do you say it? Like that. Oh, that's too big. Tiny. Medium. Like this is supposed to say the position. I'm not sure why there's no edge there. Whatever. there's
It's
like
okay.
there's
It's-
all that little bugs all
It's
over.
okay. It's okay. Thank you.
All right. So those are the causal graph. This is like this is a combo example that has like 3 kind of edges and 3 all in the same place. So it's a evolution causal branchial graph, where the branchial we refer to the events. You can also do the branchial between states, but I don't know how to call it. But this is just like 3 types of edges in the same place. So if you draw it in the usual layered way, there's going to be, it's not clear that this overlap. There's an edge from here. So it's like a complete graph between these 2 events, 3 events. And there's no graphs here, so they not really ambiguous. So it's like a same branch. This can be in the same branch like this one. But here, if you mouse over, look at this 3 position. You see there's 3 position 3, 3, and this position 3 position is 3, 1. So in a way they, hold on, they should be, yeah, they basically intersect. So they have the common root. So that maybe indicates that they're in the same. Actually, hold on, I'm a bit confused. Why there's no 2, 1, 2, 2? Maybe it's not about. now I'm confused myself. What is the condition for determining this edge? Okay, let's not go over it. The causal branchial, the causal edges are, the causal branchial edges are kind of weird. It's just a fun construction that was implemented. Like this, like another type of things you can do, where it's like this is the states graph. I think I already showed it. It's like an evolution graph, but with the but with default merging of the same of the same states. So there's like multiple edges now have the same output. We create a single state for it, and this causal states graph is just basically this one, but with different rendering of edges, where the edge rendered as a causal graph of all the past causal column. So it's like shows what would be the, though it's not very well defined, so I'm not gonna just, I'm not sure how to well define it, because there's actually multiple paths and they can all produce different causal graphs. So the fact that there's one, maybe it's not correct. It may be configured as a union of all possible ones, or maybe it should draw multiple different causal graphs, because there are multiple paths that can reach this particular state. Yeah, but at the end of the day, it's just another graph construction, and there are a lot of them. For example, another one is what we call a token when graph. Now it's like a completely different story when there's no states. We decompose the state into all individual tokens, and tokens in case of hypergraphs are edges like this. So this is one edge in this hypergraph. So it's one character in the string with some links information. The events also, in this case, show what are the inputs, not just one state, but all the tokens that get involved in that event, something like that, right? So the top one shows all the tokens, the input tokens, and the bottom shows all the output tokens. So it's like just this is like the whole function, which is a bit more general, or token when graph, which tries to even generalize it even further with a whole bunch of things. What are the tokens and how you can rewrite expressions with multiple rules, with multiple outputs, with a bunch of options, which I'm not going to go into detail right now, but you can check this out. Okay. Question here. When do you use the branchial causal graph? All right, so that's the physical question here. So that's the physics. So that's where we're still arguing about. Like, it's not really that we use the branchial graphs in the terms of this ancestor information, it kind of makes sense because you think of the states of the multiway system similarly how you think of states in quantum systems. So I think it's a configuration space, and there's some kind of evolution going on, and branchial edge formulated in this ancestry way kind of indicates some form of superposition. Who knows, right? So that's the intuition to call this quantum. But if you like read Jonathan's papers about the original one, he calls about this branch-like separation, and that is defined for events, right? So it's like an additional distance and additional measure between events that you can construct and somehow reconstruct the whole Hilbert space out of it. So it's a bit different notions going around and it's still confusing. That's why Steven's talking about Wolfram Physics Project version 2, where we actually, when we have to actually figure it out and clean it up. But right now there's like two notions floating around of the branchial graphs and how they actually connect to physics and quantum mechanics and quantum theory in particular. It's not clear at all. And maybe it's like not related to quantum theory at all in any way, and there's some better notion that we have to introduce instead of these branchial things. Yeah.
Is there a current notion of edge counting within here that's generally agreed upon, or is it still kind of up in the air? Because Stephen was talking a little bit about counting edges to try to infer energy.
Yeah, this is another confusion. Yeah, well, I think the only thing that we actually agree on is the notion of the causal graph and the algorithmic causal sets. So it's like, okay, the space-time is the causal graph, right? And the way this causal graph is constructed is algorithmically. So from some kind of computational procedure like hypergraph rewriting or any other kind of computational procedure, you just update your state and make a record of all the events, updating rules happening, draw some dependency connection between them, and that's basically all the causal information you have in the system. And that's the discrete notion of the space-time that we have. And then the question is whether this particular construction limits to some space-time or not at the end. But at least that we agree on. But as soon as we talk about quantum theory and all that, that's not agreed at all.
So nothing's changed for 100 years.
Yeah. So we can, it's basically there's some arguing going on back and forth. It's like how to actually reconstruct some quantum notions from this branchial graphs or multiway system in general. It's not clear.
Nick, I have a more pedestrian question. Can you scroll back down to the more? Yeah, here. Sorry. I'm just curious about like the token for the B, I guess up in the upper left of this plot. Why is the anchor 3B and then to 0? Why is 0 there for like, is it?
Oh, because it's because we. Oops.
Because I understand like 1A2, 2A3, but then why, like we're anchored at 3 and then or something, and then we go to 0, but I don't know why we're going to 0.
Because we have this string, right? And
yeah,
we turn it into linked hypergraph, and that's just the construction we do. We just the end of the string is 0.
Okay, so it's just convention. End of string is 0.
Yeah.
Okay.
That's this basically the last character has this child as a 0. It doesn't have to be there, I guess.
I see. Oh, because it doesn't have another character, so maybe 0 is a good convention. Okay.
Right. This is like more. This is a good example that because Steven, together with William, had a nice blog a few months ago about inventions in cellular automaton. Like this is the link to the blog. They have a more advanced version of this graph. It's like a token event graph version of multiway system, where now you can decompose your cellular automatons, in this case, game of life, two-dimensional cellular automaton into tokens. And now your definition of token is a bit more advanced. It's some kind of causal independent structure that you can isolate out from other structures in your grid, and you can call it a token, and you can show how they evolve independently. So in the blog they have like pictures like this more complicated. So you can think of them as an example of token event graphs without events. In this case, you just drop the events. Here, you kind of show by event where these tokens have been interacting, right? So there's like two causally disconnected pieces. There's some particular, I'm not going to remember how it works, but yeah, you can decompose this your grid into multiple disconnected pieces. That's the point. Okay. Ignore it. All right. If there's no, how am I think I have time. All right. There's another thing you can do with multi-computation. Instead of just, which may be a little bit more clear in terms of explanation what's going on with the causal graphs and all that. It's just when you apply this notion to just usual like arithmetic of kind of whole arbitrary language code. For example, there's a function called trace causal graph, which just directly makes a causal graph out of some evaluation of a piece of a snippet of the code in the Wolfram language. So it traces the execution of it, and it knows about what an actual events happen. So it's a single-way causal graph. So it's a nice example of the real-life single-way causal graph when you don't think about hypergraphs being written, but now it's like some particular code being run by some underlying kernel, in this case Wolfram language kernel. And this shows you that you can evaluate two space-like separated parts of the expression. So these events would be space-like separated, so there's no causal dependency between them. You can either evaluate this part or you can evaluate the right part. Here you already see that the free was evaluated, but the events are, because it shows the global expression. So it shows that there's an expression globally already existing. It contained a part of expression that was pre-evaluated, but this particular event acted on a second part, right? And then you combine them again. So this last event is causally dependent on this previous two, right? But you can similarly apply this idea to expressions, but evaluate them in the multiway fashion. Like what would happen? Like here you also have, like I have this multi-evaluate function, which does this version of evaluating expressions, but has the similar options that we have above for the multiway systems, even more. Like this is like an extra thing that you have to specify in order to say actually I want to evaluate pluses, because there's no rule associated to the plus of integers. I have to specify that, okay, I want to evaluate plus of integers through the kernel. So it's a bit like extra, but you can see that you can construct this multiway trees out of simple expressions. Like here, it shows like separate branches and that get to the same result, right? So that's an example of multiway tree when there's some ambiguity where things being evaluated first and all that. Right, there's like a notion of evolution graphs with merging. So it's basically take the tree and merge some of the states together. You can extract all the events. Now it's a multi-way causal graph because now you have branch-like separated events. So they have the events that happen on different branches. So that's like a very similar notion above, but a bit more pedestrian. So it's like just evolution without rewriting. So there's a whole blog that we wrote together with Steven a couple of years ago about expression evaluation and how it relates to physics, because we deal with the same kind of constructs of graphs, causal graphs and evolution graphs. So check it out. So, okay. Do we have to check the chat? Or whatever we're talking about is not important?
I think we're talking about interpretations, but still seem up for interpretation.
Interpretation of branchial graphs. Well, we can discuss it. That's like I'm happy to like end this lecture now and we can just discuss the interpretation if you want, right? Because this like I think it's like we're going deeper and deeper, and I'm afraid it's like becoming more and more boring, right? So feel free to just ask questions and we start discussing at this point. Thanks, John. Okay.
I have an extremely pedestrian question. So at the beginning, I asked whether the updating rule would apply to like an undirected, just an ordinary graph, not a hypergraph. I have been fiddling around in the background, and I'm struggling to get.
Hi, can you hear me? Nope.
Sorry.
Nobody.
Go on slow. Continue asking the question.
Sorry, I'm struggling to see how to get the Wolfram model plot resource function to apply to just an ordinary graph.
No, let me.
It seems to only want to work with hypergraphs that are directed.
Well, as I showed you, you have to like construct this kind of structure in order for the Wolfram model plot to understand. If you really want to use, though it's not really, so it's like, why would you use it if you already have graphs, right? So maybe it's a bit overkill, but in general, yeah, you have to turn your edges into a list of vertices in order to for Wolfram model plot to understand. Yes, so go ahead.
Yes, thank you, Nick. I have a question about the interpretation of what we are studying. In addition to physics, where could this be applied? I think this could be applied in knots, for example, but I am not sure about it, and I would like to know where could this be applied in addition to physics.
Well, I think that it's like physics is I think it's even more complicated than other another fields that you can apply it in. Usually, multiway systems is very ubiquitous. It's like whenever you have an ambiguity of your system, it's like you applying it. It's not like an application. It's like more of a way of thinking and a kind of data structure, and what it's more like a framework in the language. So it's a list of terms that we like to use. So multiway systems is, for example, can be applied to games because you have an ambiguity of players taking turns. Steven wrote a piece about games and number multiway systems. Yeah, right. Check. What kind of, is there a category that has about multiway? Like nested recursive functions. Maybe it's like here, for example, like a multiway system of applying a function. Because yeah, in a different way. What else? Where's the game one? Games and puzzles. I think there is a nice plot about with a tic-tac-toe game. This is a multiway system. So it's not like an application, it's just a way of thinking and a language. So you're not like solving some problem with this particular way of thinking and having this as graphs immediately.
Okay, thank you, got it.
No problem. Yeah. So that's what Steven calls rheology, by the way. It's like as soon as you have types of systems that you're interested in, and you want to investigate it and understand them better, this is just you can immediately employ this kind of language and the tools that we build in order to understand it better. It's not to like immediately provide you with some hammer that you can smash and immediately solve some millennial price problem, but it will help you to understand this system better, right? And what we are hoping with it that it will also help us to understand physics better, because as soon as you think it in these terms and define all your terms correctly, maybe we can say something interesting about physics too. So that's the hope, right? So I'm gonna publish this notebook, by the way, so that it's available with all the, actually ended up not using this particular section as I hoped. It's just like interspersed between the notebook. I'm gonna delete it.
I was going to say, Nick, you actually had some previous talks covering some of this material. I think's up on the Institute's YouTube.
Yeah, I think so. Yeah, I'm like the winter school. I basically did something similar. I'm trying to be different each time, depending on what your needs are currently, or what maybe some new developments been done recently. Maybe I'll try to cover those things like that. So yes, please check out some previous Wolfram Physics Project tools, live explorations. Yeah, I'm not gonna. I think I've talked about this data structure of multi-evaluation previously. I'm not gonna talk about it now unless people really want it. But it is in this notebook. I just included it just in case. But yeah, I think I covered most of the topics people care about. Because yeah, or if you care about anything else, we have still time. So go ahead.
I don't know if my audio is working right now. Can you hear me?
No, it's good.
Oh my god. All right. Nice. Took me 1.5 hours. The causal graph above, that was really confusing. Could we maybe try to like figure this out together?
There are a lot of causal there.
The one under causal branchial, there was like another one
Yep, let's find it.
where it was like, why does it look like that? Further down.
Not this one.
No.
Maybe
Further.
maybe
This
this
one.
one.
Yeah. So we know
Well,
the first level.
the branchial
right?
edges were also confusing. I hope you're not concerned about those. We just
Okay.
ignore them.
Like for example, what I don't fully understand. So the red edges are the causal graph edges, correct?
Yes. So the
Yeah.
dependent. Mhm.
So if I look like just at the middle, like just going down straight the middle to like yeah, exactly there. Like there is no connection, causal connection from what I can tell. Which is like, how is that possible?
So this event. So look, let's see. Let's try to traverse what happened. So it uses this particular rule because this input to this rule already was available at the beginning, right? So the fact that there's some other events that took this first A as an input, like this event, for example, right? And they're not space-like separated because they can be run in parallel and independent of each other. So this event, because it acts on this AB that were already available, can be run at any point before. The fact that it we put this in the graph in this particular order doesn't matter because there's no actual causal link between them. So if you can probably find an analog of this, because this event is here purely because the global state includes this left AA string already. But there's like an alternative event here, for example, that applied the same rule to the same place, but immediately, right? So in a way, this event is completely analogous to this event because actually what happens locally is the same. It's just only the global background changed because in this particular thing, we like to render the global state of this particular point. But an actual event only is local, right? So it only rewrites part of the string. I don't know whether it answers, but it's like, yeah, just think of it that there's no connection to any other event in this picture. It's either in the separate branch or there's completely spatially independent, acts on different characters.
Wait, so if I understand you correctly, it's because it appeared beforehand, it's not a global event and doesn't matter. But then I look at the one further to the right, yeah, where your cursor was, just a little up. And there the ABBA, if you go further, 3 to the right.
Like this one?
Yeah, that one, yeah. That looks very similar to that one is causally connected, but it looks very similar to
Well, it looks very similar, but it acts on a separate branch. So it's like a completely independent branch-wise. So technically there's maybe a branchial edge between those but I'm not sure there should be. But yeah, in a way, this is like one space-time. This is another space-time. So they're completely branchially separated. because in the beginning you had some ambiguity on what rule to apply. Like what they apply this rule to this right side of the string, or this rule to the left side, or to this A. That's why it actually is ambiguous, because they overlap. And when they're overlap, you can think of it as like a separate branch creates for both outcomes. And all the further events in these branches would be completely independent. So there's not going to be a link between them.
Oh, I see. Like the middle one only has the A to AA. No, that doesn't it either. Because he also never mind. Okay, I don't understand.
It's tricky. It's like another way of thinking about it. Like, okay, each event has a lot of metadata. Like this, like in the tooltip there, shows all the information that can decide whether two events dependent or not. So another condition, one condition is like whether the input of one event is also overlaps with some output with another event. That's one condition, right? So we have input and output there. Those reference some particular characters or some edges or vertices, right? Another thing, there's like a step. So you want a causal dependency between events that have like on a different steps, right? Because you evaluated it, so you want one step larger than another step, or something like that. And another condition is that this tree position over there that I already talked about it. The tree position tells you about where those events are on the whole multiway tree. So if events on the multiway tree are in the separate branches, you don't connect them with any dependency. So it's like the first thing you have to do is to only take events on the same branch, right? It's just one branch of the tree. So in the tree, they look like as a sequence of events, but actually some of them may be time-like separated, some can be space-like separated. But the first step is just to identify what branch are you working in. Like take all the edges in particular branch, put them in a bag, and then look what would be actual space-like and time-like separation between those events. And then you can construct a single-way causal graph for this particular branch. Right? But if you want like the whole multiway picture, it's a bit confusing when you combine all of these events together like we do here, because this shows events across all the branches. So that's why it's not very clear that when you have like absolutely similar events happening and there's no links between them. But you can think of it as just like a union of all those single way causal graphs for each branch of the tree. I don't know. So I'm not sure whether it helps. I'm happy to clarify more if I knew how.
Is only the red edges part of the causal graph, or are the red edges additionally to the gray edges in the causal graph?
Causal graph just contains by construction only like orange edges. So those are the dependency links, only the causal links, right? So the causal graphs without any other prefix like evolution or branchial just contains events and there are causal links between them. Right. Another thing you can add to make it more clear, like you can add this extra initial event. It's like the Big Bang, so to speak. It's like the event that produces initial conditions, right? So that's like a special event that from nothing creates this initial string, right? So just one event that all the other events going to be dependent on, so that it's like, so that graph is not disconnected. Makes it more clear. But there's like many events. Yeah.
So I'm sorry to interrupt, but so we can kind of think of the causal graph as the inheritance criteria for the future events?
Not necessarily future, right? Just all the events. It's like you can put all of your events into a bag, and if you know whether they use the same vertices, so that like input and output of one overlap, you can draw a causal link between them. Right?
Okay, so it's the rule they're operating by. Cool.
Yeah. It's a very natural rule for all the computationally produced causal graphs, because they all operate on the same on the same substrate, which is like in this case it's a string or hypergraph. But as soon as there's substrate is defined and can be decomposed into different separated eames or vertices, then you can make this constraint and determine whether one event is dependent on another or not. Yeah, I know it's confusing, but maybe it takes time to completely absorb this. So I'm happy to clarify more if more direct questions about it are there.
Like, for example, if you take the second node from the left in the second row, AA, ABBA.
You can annotate your Zoom screen.
Oh.
so I encourage you to pick the pencil and just.
Oh, I see. Oh, that's
point.
nice. Didn't know that. This one, right?
Yeah.
That one comes from the previous node. Like, this doesn't come straight from this rule. Like, if I apply the rules above here, I don't get to this node. So why is there like direct connection?
You have to draw. Yeah. Okay. So this event here or here, it's you can see that there's says step arrow 2. So this event happened on the second application of your multiway system. So the fact that it appears immediately as causally dependent on this event, this Big Bang event, is purely it can be confusing, but because there's because this rewriting happened, the first actual rewriting happened on the independent part of the string, there's no causal dependency rather than this Big Bang one, right? There's another event happened that rerolled this first A into double A,
Right.
but this particular event is not dependent on it, so we can't draw a causal link to it. There's the only causal dependence is on this Big Bang one, right? Yeah, confusing, I know. That's the nature of it. You really have to play around with it, make more examples for yourself. Look at the underlying structure of events. It's a bit, and maybe print all the vertices. It's explicitly this is one event, and it's very complicated. This is all the input string, the output string, already formulated as a linked hypergraph. This is what links it took as an input, what links it produced as an output, which rule we used out of these two. The position is basically the edges that were involved in that particular list. 2 and 3 means this edges. I think that's what position means. I'm not even sure. I haven't reviewed this particular encoding myself this time. Match position, I guess you can ignore it because that I think it corresponds to the hypergraph itself, and it's always going to be 1, so it's kind of boring. This is also going to be ignored. This is the step, because we did 2 steps. Some of the events happened on the first step, some of the events happened on the second step. This is 3 position that indicates this is the list of positions. So if it happens on the first step, it's going to be an integer of length, a list of length 1. Oh, right, length 1, but there's going to be 3 of them because there are 3 different applications that could have happened on the first step. On the second step, there's going to be, you just extend your tree position because you're going deeper. So this is going deeper into the tree. So this is this particular event and this particular event were siblings, right? So they happened on the same branch, but we had an additional ambiguity which one of them applied. So there's 3 siblings and so on. you can decompose all of it and start reasoning about those. But in practice, usually it doesn't matter anyway. It's nobody but the programmer would care about this kind of things as soon as you frame it as an application, but it's not clear what the application of these tools actually is. The only application is just the framework itself, how we can reason about it for physics games and so on. But usually you just write your own tools, otherwise you're not going to understand anything.
All right, with that, we should end soon. Thanks a lot, Nick, and thanks everyone for all your questions and interactions. In about 45 minutes, we'll begin the talk on computational biology and rewriting, so be there for that. Thank you, everyone. See you. Bye-bye.
Thank you, Churches. Thank you, Nick. Bye.
Thanks, everybody. Thanks, Nick.